Right, we are going to spend some time on analyzing RC circuits. So these are circuits, these are DC circuits that contain a capacitor as a circuit element. So we have a capacitor, but in addition to the capacitor, we have resistors and the EMF devices. These kind of circuits actually is something that we have met when we are charging a capacitor. And discharging a capacitor. So these are the two situations that we meet these circuits. But up to now we haven't said anything about the function of the resistor that might be present in the wires that we use. So here we are going to understand the function of these resistors in a better way. So the RC circuits might be as simple as these two, when you're charging a capacitor, where you have just a single loop, or discharging, right? There's a single loop in here. So it is easier to write down the circuit equations for these two cases. But in principle, we might have a very complicated RC circuit as well. With the techniques that we are going to learn in here, you will be able to write down the circuit equations for these kind of complicated circuits as well. But unfortunately, the equations will be very complicated. So they are going to be differential equations, which are kind of hard to solve. So as a result, we are not going to analyze these kind of circuits in here. But for actually asking for some simple questions, I'm going to give some examples from these complicated RC circuits. Okay, but our main job is to actually analyze this charging circuit. So I'm going to start with this one. But before discussing this, let's say something about the relevant variables that we are going to use when we are writing the circuit equations. So one of them is the charge on the capacitor. So that's an important quantity. Let's just note that, let's remember that the capacitor has two plates, and if there is a charge Q on one of the plates, then the other plate should have a charge minus Q, so that the whole capacitor is charge neutral. So as a result, when you are talking about the charge on a capacitor, we always mean the charge on a plate, and you have to specify which plate is this. So that's one of the important things. So in that case, for example, on this picture, we have an upper plate and a lower plate. I have specified the charge on the upper plate as Q, right? So that's the variable that I use. So I have to show in which plate this charge refers to. Since this is a variable, this variable can be positive as well as negative, so it can be a negative quantity as well. So don't get confused by using plus Q and minus Q used as variables. So whenever I say plus Q, I don't imply that Q has to be a positive quantity, because I'm going to write down some equations that involve this variable. Those equations will be valid independent of the sign of the charge. Okay, let's also remember the current convention. So when I'm specifying a current on a branch of a circuit, I have to specify in which direction. So I have to choose a direction and then say that the current on that branch is along that direction is I. So this is kind of a similar thing, right? The charge on you have to specify what Q refers to, in which plate is this Q is residing on, and I have to specify in which direction this current is flowing to. So the next thing is this, there's a current flowing to that plate in here, and of course this current is carrying charges to that plate, so that means this charge on that plate is going to change. So we have to then understand the relationship between the current and the charge. And so that's basically the relationship between, versus is not a good word in here, the relationship between the current quantity and the charge quantity relation. For the previous picture, of course, this is actually quite easy to understand, right? Let's just draw this again. So there's a current flowing on this branch, and this current is carrying charges, and these charges are piling up on the upper plate of the capacitor. So therefore, the rate of change of that charge on the upper plate should be equal to the current. Okay, this is one of the equations that we are going to write down, but there are some details in here, so that's not a given equation that you can mindlessly write down. You have to be careful with this. But before talking about these kind of things, let me talk about the current in the other plate. So let's remember, let me use a different color for this one. I'm going to use a white color. So on the other plate, the charge is minus Q. So as a result, I can think about a similar kind of a situation. If I draw the arrow towards the plate and call the current on that branch along that direction as I prime, in that case, the rate of change of the charge on the plate, which is minus Q, the rate of change is the time derivative of this thing is equal to I prime, therefore. So I can therefore write down the current on the other branch in here, on this branch, as a time derivative of the charge on the other plate. And since there's a negative sign in here, so that's minus dq over dt, that's I prime. But I have said that the dq over dt is the current on the other branch, so therefore this is minus I. Okay, so therefore the current that's flowing to the other plate should be related to the current that's flowing to the upper plate, and they have to be equal and opposite. But of course, the sign depends on how I choose my directions. So as a result, for the current in that branch, if I have chosen the direction of the arrow in the downward direction, so if it is in this direction, in that case, I would say that the current in here would be I again. All right, so let's just, this is a very important point, so let's repeat this argument again. Okay. I'm drawing an arrow in here. I say that the current flowing to the upper plate is I. In that case, the current flowing in the other branch, which is connected to the opposite plate of the capacitor, but in the same direction, should also be the same. It's kind of interesting because this looks like the rule that we have used when we have discussed the current at different points of the same wire. We have said that at two different points of the wire, the currents should be the same, provided that, of course, the same directions are chosen. We have a similar kind of a thing in here, right? So the same rule seems to be true, even if there are some capacitors somewhere on the branch. So the existence of the capacitor somehow does not change that rule. The reason is that the capacitor as a total should be charge neutral. So even though there's a charge pileup on the plates, the whole capacitor is charge neutral. So this whole thing is charge neutral, and so therefore there is no charge pileup in that region in here. So therefore, whatever the current is flowing downward in here is going to continue in the rest of the branch. So you can think of it like this. This is kind of an unusual situation where you have a current flowing in this part of the branch. There's a current flowing in here. Somehow that current stops in here and it continues from the other part of the circuit. So there is no current that is flowing in between the place of the capacitor. There is no current there, but somehow the same current continues in this upper branch of the wire and the lower branch of the wire. That's kind of an unusual situation, but of course, once you accept this, you are going to get used to this. Okay, Let's then talk about the other cases. So I have said that there are some directions in there. So let's talk about the situation. Sometimes we just call the charge on this plate as Q, but we choose the current on the branch by using an arrow like that. So the current is I along that direction. So in that case, what is the relationship between that relates the current to that charge? This is simple, but you have to be, of course, careful with this. So either you can use the upper plate or the lower plate. So for the lower plate, all you need to think is this. The lower plate has a charge minus Q and a current I flowing to it. So therefore, this I should be equal to the rate of change of the minus Q, right? So therefore, this is the relationship. Or you can use this upper plate, right? In that case, there's a charge Q on the plate, and the current I is flowing away from it. But this is equivalent to a current minus I flowing towards a plate. So therefore, the current that flows towards the plate, which is minus I, is equal to dq over the rate of change of the charge on the plate, right? So in either case, of course, you are going to get the same relationship. So as a result, for this special case, for these choices, therefore the current is not equal to dq over dt. There is a minus sign in front of it. So that's one of the things that you have to be careful with. So with this choice of the charge on a plate and the current, the relationship between them is like that. There's a minus sign in front. But with the previous choice, where the charge is on that plate, charge is plus Q on that plate, and the current is flowing towards that plate, in that case, the relationship has a positive sign in front of it, right? Since these things, I mean, the plates and the directions are basically chosen by you in an arbitrary manner. This is one of the points that you have to be careful with. Okay. So next, writing down the loop rule. So that's I'm going to write down draw the charging circuit in here. I have a resistor, a capacitor, and an EMF device. Right? We don't have a junction rule in here, so as a result, we don't have to write it down, but we have to write down the loop rule. And for this, of course, we have to choose our variables. So let's again do it as in the previous case. So I'm going to call the current along that direction as I. I is my variable. And I'm going to call the charge on that plate as Q. So the first thing that we are going to write down is that, of course, notice that these two are not independent. Rate of change of the charge is equal to the current. So that's our first equation that relates one variable to the other one. Okay, since there is a time derivative in here, of course, we are going to get some differential equation, but we are going to talk about it at the end. So then, of course, we are going to write down the Kirchhoff's loop rule. Right? Before, when we talked about the loop rule, I said that I can write this thing down like this. This is equal to the sum of the EMFs is equal to sum of the potential drops on the resistors. But, of course, we don't have just a resistor in here. We also have a capacitor. Right? Since the capacitor side is not included on the left-hand side of that equation, so somehow I have to write down a potential drop expression on the capacitor. Usually, I'm confused with these kind of expressions. So I know how to write down a potential drop on a resistor. So that's given by the Ohm's law. That's well known. But I cannot easily remember the potential drop on a capacitor. So as a result, I always have a difficulty in writing this thing immediately. So as a result, in all these kind of situations, I just go back to the very first statement of the loop rule. This basically says that the sum of the changes in the potential is equal to 0 when you go around the loop. And that's the equation that we need to write down. So as a result, let me erase all of these things, right? I'm basically going to write this thing down. So let me carry this to the upper side in here, right? What I'm going to do is this. I'm going to travel around this loop in here, starting from a certain point. So I'm going to start from that point. Let me call that point as A, and this point as B, and that point as C. This point as the same point as A, so let me also call this as A as well. I'll just go around this loop, and I'm just going to write down the changes in the potential that I meet when I travel. So I'll start from A. So first I move from A to B. So as a result, I'm going to meet a change in potential, which is VB minus VA. And then I'm going to have a change in potential VC minus VB. And then finally, I'm going to have a change in potential VA minus VC. So sum of all of these should be equal to 0. Let me again explain what these things are. When I use a double subscript, it's always the difference of these subscripts, but in the order given. So that's the convention that I use. So when I write VAC, this is VA minus VC. It's not VC minus VA. Just be careful with this. So as a result, I have an expression in here which is of that form. But you can easily check that everything in here cancels with something else. So as a result, it is quite easy to see that this whole thing is equal to 0. Right? So that's the first thing that I should note. But I'm going to now write them down. So this is kind of it's a slow way of writing the loop rule, but that's kind of a sure way, because by using these directions you can understand which one is which. So VBA, for example, is the potential difference across the terminals of an EMF device. I know that EMF is a positive quantity, so therefore B is at a higher potential than A. So therefore this is a positive quantity, so that's the EMF. Now I'm going to write down VCB. I'm just going to think of it like this. If the current is positive, then C would be at a lower potential than B. So therefore VCB would be negative, right? Because the potential drops in the direction of the positive current. So therefore, if the current is positive, this quantity would be negative. So therefore, I place a minus sign in front. So that's the next thing. And finally, VAC. Again, I'm going to think of this in the same way. If the charge is positive, in that case, C will be at a higher potential than A, right? So therefore, VAC would be negative. So if Q is positive, that quantity should be negative. So therefore, I put a minus sign in front, right? Or if you want to, you just write down the expression for VCA. You just say that the VCA is equal to Q divided by C. That's basically the capacitor equations. The charge on the capacitor is equal to capacitance times the potential difference across the plates. So as a result, you just write it down like that. So therefore, this is our circuit equation. This is the loop rule equation. Okay. As I have said before, you can express it like this. This is EMF is equal to I times R plus Q over C. And some people would like to think of the first term as the potential drop on the resistor, and the second term as the potential drop on the capacitor. But I mean, whether this is positive or negative depends on which plate you have chosen this charge to refer to. So as a result, it's not actually quite easy to see. And for this reason, I don't want to use these kind of expressions because it always confuses me.